Hey, algebra. Hashtag slope due to awareness. So for the do now today, just draw a quick sketch. Give me a line with a positive slope and a line with a negative slope. And you can hit pause on the video until you got those drawn. All right, well, the positive line is going to be going up. The negative slope is going to be going down. So the negative line, as the graph walker is moving from the left side across to the right side, is going to be going down. Right. Sometimes people like to say, well, what if you drew the graph walker over here and then you was walking the other direction? Wouldn't you be going up this positive? Which is not wrong, but that is not the way we read graphs. Right. So in math, we always read graphs from the left side going across to the right. So this green one would be going down, and the blue one here will be going up. So positive slope, negative slope. Well, today we're going to look at data correlation. We'll start off by introducing this idea of a scatter plot. So our learning target for today will be able to classify the correlation between two data sets. There are three main reasons why we study lines. And this is something which I know a lot of people always want to know, like, why are we learning this? And I'm sure these reasons are probably not explained often enough, but here they are. We study lines in math class because of these three reasons: identifying patterns, establishing relationships, making predictions. So far, really, we've only focused on that one. We've identified patterns. But the third one, making predictions, we have really not touched on at all. That's where we're heading now. So if we can use math to identify patterns, that's great. If we can establish some relationships, that gives a little bit of meaning to it. But really, there's really not that. Why are we learning this? It's just like, okay, these things are true, but what do I need to know it for? Well, the reason why many people use math in their careers and in their jobs is for this last reason, so that we can, once we've established the pattern in the relationship, now we can use it to make a prediction about what's going to happen in this situation or that situation. So that's where we're heading. Okay, so we got some vocabulary to look at, causation and correlation. So let's get some definitions. Causation is when one event directly causes an effect to occur. Okay, it's the exact same effect every single time. The effect depends on the cause, and it is quantifiable. We can put a number on it. So this would be like if you have a job where you get paid, $10 every hour. It's determined by how many hours you work, and that's going to cause an effect on the size of your paycheck, how much you get paid. It happens exactly the same way every single time. And if we made a graph, it would give us a perfectly straight line. Every time you go over 1 hour on the graph, it goes up by $10. Correlation. Okay, so correlation is kind of this new thing we haven't seen before. Correlation is where we have two events that are usually paired together and occur as a pair, but it's not going to give us the perfectly straight line on the graph. So there's not a clear quantifiable cause and effect. So you can say, hey, if I study more, my grade goes up. But sometimes I have to study a lot more and my grade only goes up a little. Sometimes I can study just a little bit, but my grade goes up a lot. And so it's not exactly the same thing every single time. We can't put a quantifiable number or a measurement on it, but we can still see, what? The more I do this thing, the more that other thing happens. So there's a relationship there. They're definitely connected, but it's not going to give us a perfectly straight line if we were to graph it. We'll see some examples of that in just a minute. Okay, so moving on. Here we go. Three types of data sets we're going to study. Causation is the first one. We've seen that a lot already this year. And at this stage of the game, we're not going to see a whole lot of causation because usually when we're gathering data to put together data sets, usually we don't get causation. Also, we've already seen that a ton, and it's something that we can deal with. If our graph makes a straight line, like, we know what to do with that. Okay, but still we need to know causation. Causation on the graph is going to give us a perfectly straight line. We can describe that straight line as having a slope, which is either positive or negative, depending on whether it's going up or down. And so there's a thing called a correlation coefficient. Okay, the causation relationship is going to have a correlation coefficient of exactly +1 if it's going up, or -1 if it is going down. right? So positive and negative just tell you the slope, and it's not an actual measurement of slope because we're not counting the rise and the run. We're just saying, look, if it's a perfectly straight line going up, that's called the correlation of +1. If it's a perfectly straight line going down, it's a correlation of -1. Okay, so that's causation. Next up is correlation, where these two things are related. We'll see what that looks like on a graph in just a minute. A correlation can be either positive or negative, depending on whether the shape of the dots on the graph are heading up, that would be positive, or heading down, that would be negative. And then we further describe correlation by either strong or weak. Strong means that the dots on our graph are much closer to being in a perfect straight line. It's not perfect, but they're really close to it. And that'll have a correlation coefficient, the number, that's close to 1. So like 0.9. It could be +1, it could be -1, depending on whether it's going up or going down. Right? A weak correlation is going to be something where you can look at the graph and you can totally tell it's going in this direction. It's going up or it's going down, but those dots still are pretty scattered around and not close to a straight line. Okay, so we'd call that a weak correlation. As long as it's still visible, you can tell, okay, the dots are going up or the dots are going down in general, then it's going to have some kind of correlation. But the weak correlation, we're going to give a much smaller correlation coefficient to that. So it could be something like 0.5. That's not the only option. It could be 0.4, it could be 0.3. We could have a whole bunch of decimal places, but around 0.5. And then lastly, we might have no correlation. So we'll see the examples of all of these in just a minute. But if there is no correlation, then the correlation coefficient is going to equal 0. There's no correlation. Okay. So here's what the graphs look like. First of all, scatter plot is a type of graph where we just put dots. We're plotting data, so you've got two different measurements on your two different axes. Okay, so these are both examples of scatter plots. Dots on a graph, we never connect the dots. Right, that's not what you do with a scatter plot, it's just dots. All right, so let's see some examples of these different kinds of correlations. So here are two positive correlations. I've got a weak positive correlation. I can totally tell that the dots are trending upward as I go across the graph. So it's a positive correlation. There is definitely a correlation there, but these dots are still pretty spread apart as they go up. And so it's going to be a weak positive correlation. The easiest way for me to explain the difference between a weak positive correlation and a strong positive correlation is you can just visualize this. Draw a rectangle around the dots, the smallest possible rectangle around all the dots. You don't have to actually draw it. I will right now, but you can just visualize smallest possible rectangle that goes around all of the dots. Okay, so in both cases, we can see the rectangle is slanted and is pointing uphill. So that tells us that they're both positive. The weak positive correlation, that rectangle is much wider, right? And the strong positive correlation, that rectangle is really skinny, right? So if the rectangle is really skinny, that's indicative that it's a strong correlation. If the rectangle is wide, then that is a weak correlation. Just for clarification here, the width I'm talking about is measured this way. The other axis would be length. Okay, so the red one is much wider, the blue one is much narrower. So that's the difference between weak and strong. So here's some negative correlations. The same idea, except these are both going down. So that tells us that they are negative. And I could do the same approach here if I draw the smallest possible rectangle around these dots and the smallest possible rectangle around these dots. The green one is much wider, the red one is much narrower. Okay, narrow rectangles are going to indicate a strong correlation. The wide rectangle is going to show us a weak correlation. Both of them very visibly are heading down, so that is a negative correlation. Okay, no correlation just means we have a scatter plot and we have absolutely no idea whether the dots are heading in one direction or another. Right? You can't tell, as I go across the graph from left to right, are the dots heading up or are they heading down? I don't know. It looks like just a bunch of random dots, right? And that's true in both graphs. It's just a bunch of random dots. There doesn't seem to be any pattern. Are they going up? Are they going down? Can't tell. So that's no correlation. Okay, causation, again, we're not going to see this very much in our data collection, but it's going to be a perfectly straight line. These do show the dots connected, which is a thing we can do if it's causation, because it is a perfectly straight line. So positive causation is going to be going up with a positive slope. We're not actually measuring what the slope is. We're just saying if it is going up, that's positive, and the negative causation is a perfectly straight line, but it's going down. Okay, so I'm going to back up 1 second here. So one of the things that we do is to describe a correlation, we put a number on that correlation. It's called the correlation coefficient, right? So causation is going to be a perfectly straight line, and so that gets a value of either +1 or -1. So it's not actually measuring the slope. The positive or negative tells you the direction it's going, but the 1 just means it's a perfect straight line. And then no correlation, you can have a correlation coefficient of 0 because no correlation. Okay, so a strong and a weak correlation are going to be somewhere in between 0 and 1 if it's positive. It's going to be somewhere between 0 and -1 if it's a negative correlation. Okay, so again, I gave the examples of 0.9 for strong and 0.5 for weak. Those are not the only possible answers, right? So you could have any decimal value between 0 and 1 or between 0 and -1. Okay, so if I was going to put some correlation coefficients on these same graphs that we just saw, this red one, so the correlation coefficient usually is given the letter R. You don't need to really remember that probably for any reason, but I would say this is probably about 0.5 because the dots are fairly spread apart and we've described it as weak. Usually we're going to describe weak correlation as about 0.5. It's positive, and so since the shape of the dots is going up, it's a positive correlation. They're going to have a positive coefficient. For the blue one, as I said earlier, probably is going to be a 0.9. It's positive because the shape of the dots are going uphill, so that's a positive slope. It's a positive correlation, and it's really, really close to being a perfect straight line. It's clearly not perfect, but it's very close. So the 0.9 is going to be really close to a perfect straight line. All right, so the green one is going to be negative because this is a negative correlation, so it's going downhill, so I'm going to have a negative correlation coefficient. These dots, I think, are more spread out than the weak positive correlation we just saw on the previous screen. So I might call this a negative 0.4. It's a smaller number, negative still, because it's a negative correlation, but the value is closer to 0. And this red one also will be negative because it's going down, but these dots are not quite as close to being a perfect straight line as the strong positive correlation on the previous screen was. So I might call this one negative 0.8. Okay, and this might seem kind of like arbitrary. It's totally arbitrary at this point. Mathematicians actually have ways to calculate the correlation coefficient to come up with the actual value of, like, well, is this actually a negative 0.8 or is it actually a 0.9? Right? There's a way to calculate that, and it is way beyond the scope of what we're learning in this class. So we're just trying to get kind of ballpark so that we can guess and put some labels that are kind of close. All right, no correlation. If there's no correlation, R is going to be 0. That would be true for both of these, because there is no correlation on either of those graphs. With the causation, the blue one, positive, it's a perfect straight line, so 1. And with the red one, since it is going down, that'll be negative, but it's a perfect straight line, so a value of -1. All right, so same idea here. Let's match. Here are 4 scatter plots. Okay, let's just look at 2 at a time here. Match each scatter plot below with one of the 4 specified correlation values. So here's my 4 different correlation coefficients to choose from: negative 0.47, negative 0.89, positive 0.91, and positive 0.12. All right. So here's all 4 of them. The top 2 seem to be much less like lines. They just look like kind of blobs of dots, right? So I'm thinking I probably want these two options to go with the bottom two possibilities down here because they are much closer to a value of +1 and -1. So you're going to get a graph that is much closer to a straight line. Okay, let's save those for just a minute. So I am left with these two options, -0.47 and and +0.12. So I'm looking at my two graphs. The first graph here really doesn't look like much of any kind of pattern. It really looks like there's not a correlation. And so I would choose the number closest to 0. So out of the four options I had, this one is closest to 0. It is, since it was given to me as an option, all right, would I come up with this on my own? No, I probably would have just called it 0 if I was doing this on my own. But that was the option I had to choose from. Okay, it kind of looks like maybe the dots are sort of a tiny bit trending. If I'm drawing a rectangle here, kind of aimed uphill a little bit. So I could see that this might be a positive value. Right. This graph, if I do my rectangle, somehow I got a dotted line. The dots do seem to be clearly showing a pattern. The dots are, that's a pretty wide rectangle, but I can clearly see that as I go across the graph, it is heading downhill. So I know this has got to be a negative. It seems like it's pretty weak correlation, so I need a negative value. And this is close to -0.5, which we said that would be a weak correlation. Okay, so then let's look at the bottom two options. Okay, this one is clearly going downhill, so that's going to be a negative correlation. This one clearly going uphill, so that's going to be a positive correlation. So I'm going to take the positive number, put it on the positive graph, the negative correlation, put it on the negative graph. They're not straight lines, but it's a pretty strong correlation. Right? There's still some spread. If I look at the rectangle, there's definitely some width to the rectangle. It's not it's not a perfect straight line, but the relationship, the pattern, the trend, definitely on this green one is going downhill, and it's pretty tight. The width of the rectangle is pretty narrow, and the same thing for this purple one, going uphill this time, but the width of the rectangle is really pretty narrow compared to its length. Hey, so lastly, let's describe the correlation shown by each of these two scatter plots. We'll just look at one at a time, but I've got two scatter plots here. So for this first scatter plot, would you say that there is correlation or causation or none of the above? Well, it's not a perfect straight line, so it's definitely not causation. There is definitely a trend going on in the graph. I can clearly see that the dots are heading upward. So there's a correlation. That's too many L's. And the next question, if there's a correlation, is it positive or negative? Well, these dots are definitely going up, and so that'd be positive. And then the last question we'd want to ask is positive correlation, is it a weak or a strong positive correlation? Well, if I draw the smallest possible rectangle around these dots, it kind of got off just a tiny bit there. That is a very narrow rectangle. And whether you draw the rectangle in real life or just visualize, it's going to be a very narrow rectangle. The dots are very close to being a perfect straight line, but not actually a perfect straight line. So I would say it's definitely a strong positive correlation. And then if we were asked to give it a correlation value, correlation coefficient, it's going to be positive since it is a positive correlation. And strong correlation probably is going to be very close to 1, but can't be 1 because it's not a perfect straight line. So we'd call it positive 0.9. Second graph. Causation, correlation, or neither. Well, there's definitely a pattern here, so it's not going to be neither. Causation or correlation, well, it's not a perfect straight line, so it's not causation. So this one, again, correlation. Positive or negative? Well, this one is definitely going downhill, so negative. The last word description, strong or weak. That's kind of a sloppy drawing. So we put a rectangle around there. It seems that's a better drawing. Still not straight lines, but I should get a ruler if I want straight lines. It seems to me like that's still pretty strong, right? It's not as strong as the first graph that we saw, but I would not describe that as being a weak correlation. I mean, that's a pretty narrow rectangle. And then lastly, a correlation value, correlation coefficient. Well, it's got to be negative since we have a negative correlation. I probably would not call this one 0.9 if the first one was 0.9 because that graph on the left side, the dots are in that much narrower rectangle. So I probably, if I just get to make up my own number here, I'd probably call this a 0.8, negative 0.8.